Welcome to my talk titled Using Light for Communication, Showing Light the Right Path. I am Akhil. I'm a scholar at Department of Electrical Engineering. So let's get on with the talk. So the first question is, why do we even need light for communication? So if we see the current statistics, around 70% of the world population is currently using internet, currently online. And due to this, there is ever increasing demand for high capacity communication and high speed internet. And the current RF infrastructure alone won't be able to meet these high demands. So that's where optics comes to the rescue, specifically talking optical fibers. So if we see the RF spectrum here, the range of frequencies which RF uses as carriers, the frequencies range is from megahertz to gigahertz. But when we are shifting to optical communication, this carrier wave is now light, which is in nanometers of wavelengths. So that means my carrier frequency is now in terahertz. So as we increase the frequency, I get to work with more bandwidth, and I'm able to achieve higher speeds over this communication channel. So in this, in my talk, I'll be focusing more on this infrared region of this optical spectrum. Now, when it comes to optical fibers, one of the major challenge is laying the fibers themselves, because sometimes, not sometimes, mostly it is time consuming, and of course it is expensive, but sometimes it is not possible or very challenging to lay fibers in terrains which are at very difficult geographic locations. So that's where free space optics or FSO comes into picture, where the light is now not traveling inside the fiber anymore, but rather it is traveling in the free space, in the atmosphere, hence the name free space optics. For the FSO system to work, it requires just the installation of two nodes, transmitter and receiver. So due to this, the inherent challenge of laying the fibers goes away. And since the laser is now traveling in the free space, it is made sure that the laser powers are kept well within the safety limits. Now, apart from easier installation, FSO comes with a more advantage of having higher data rate of an optical fiber while having the flexibility of wireless communication, and that too it uses unlicensed spectrum. Now, to give you a taste of where is this technology currently right now. So in 2019, Germans have set up a world record of around 1.7 terabits per second free space link over several kilometers. But again, then this technology is not something which is limited to test beds or which is limited to academia inside labs, but rather actual groundwork has been happening with this technology. Like for example, in Andhra Pradesh, internet has been provided at speeds of 20 gigabits per second using free space optics. This was done in a pilot project by Google and in collaboration with Bharti Airtel. And also, if you see in this image, so this is that Sonam Wangchuk is probably pointing towards a remote school that got internet connectivity for the very first time last year due to hilltop free space optics setup. So now, as you might have guessed by now, one of the major requirement in free space optics is a line of sight between my transmitter and receiver, so that once we get this line of sight, I'll be able to get a free space optics link over which I am actually sending my communication data. So better this alignment between my transmitter and receiver, more will be the power at my receiving end, and lesser will be the bit error rate of my communication channel. So in short, for a reliable high-speed communication over free space optics, I need good alignment between the transmitter and receiver. So now the question comes is this alignment naturally stable? So let's see that, let's understand that with this small video here. So this is a small video showing a family having a nice time at beach side. So one thing to notice here is even though the camera is not moving, you are able to see a shimmering effect in the video. By shimmering, I mean the small jitterness in the video. So this is because the light rays that are traveling from this object towards the camera lens, they are not exactly traveling in a fixed straight line, but rather this path is deviating over time. So this deviation is because of the atmospheric effects of random variations in temperature, due to which my refractive index of the atmosphere keeps on changing. So even if I have a, let's say I have a free space link, I have a good initial received power, high initial received power, but over the time this received power goes on decreasing, and eventually I may lose my alignment. So in short, this alignment is indeed not naturally stable, and in fact we can say light loses its path over time. So now the next question comes in, how do we show the light the right path? So typically what we do is we give beam steering abilities to the transmitter side, as you can see in this animation, and this beam is steered in such a way that the misalignments in the beam path which were caused by the atmosphere get compensated. So this is the typical workflow of the current beam alignment or beam stabilization solutions, where the beam at the receiver side is received using an optical setup, telescope in this case, and then it goes to a beam splitter, where some part of the received beam is made to fall on a detector plate, as you can see here, and the rest of the received laser is used for the actual communication part. The other blocks you see over here are here to make sure that this beam spot is always in the middle of my detector plate. This is where the alignment is good, and this is where I receive the maximum received power. So now the problem with this current alignment solutions is the presence of this beam splitter itself. Because of this, we are unable to use the complete received power for the communication, because we are tapping out some of the power for the alignment purpose. And this can be problematic because the power at the receiver end is already very low. It's in microwatts. So that's where our solution comes in, where we are trying to align the misaligned beam by eliminating the beam splitters at the receiving end, thereby saving the last bit of power. So in our case, we are steering our beam to account for these misalignments by using the inherent nature of the laser beam itself. So this is the typical setup of the free space optics, where there's a transmitter lens which is transmitting my laser. The laser is traveling in free space, and at the receiver side there is a receiver optic sitting here to collect the laser. So now if we see the intensity variation of this laser along along the transverse plane, along any of this beam path during propagation, you will find that the intensity of this beam is varying as a Gaussian function. So this is good. This is what we want, because this tells me that there is only one maxima in the intensity, and that maximum power is at the beam center. And if I go to beam center from any direction towards the beam center, the intensity will always be increasing. So we use precisely this property to steer our beam to correct for the misalignments. Let's see that with some example. So at the receiver plane, let's just say due to the atmospheric effects, my link got misaligned a bit because still some part of the laser is falling on the receiver optical lens here. And now using optimization algorithms, I can find the direction in which the intensity of the beam is increasing. So now if I steer my beam in this direction, then I will be able to correct for the misalignment and get back my proper alignment. Now what about the second case, where the misalignment is too much and no part of the beam is falling on the receiver lens? So in this case, since there is no power at the receiver at all, I won't be able to find this direction in which my intensity is increasing. That's why we can't directly go from completely misaligned case to link recovery. So we have to go from case 2 to case 1. So how we are going from this case to this case will be clear later down the slides. Now coming to the actual test bed, we have motorized our transmitter stage using microcontrollers. This transmitter will be looking for the receiver optics in the 2D plane, and for the alignment, we are using 1310 nanometer laser, where at the transmitter side, we are biasing a laser diode, and we are sending it into free space via our optical setup. And at the receiver side, again, we are collecting the free space laser using a receiver, and then first this laser goes to a photodiode, which converts the optical intensity to electrical current. Then it goes to a transimpedance amplifier, which converts my electrical current to voltage. And now the output of this amplifier goes to another amplifier called lock-in amplifier, whose output is a DC voltage, which gives the power at the receiver end. Now this lock-in amplifier is a device which is capable of detecting noisy signals, provided we know the frequency of my desired signal beforehand. So that's why we, before sending the laser, we are modulating the alignment laser with a known frequency, and the same frequency we are giving as a reference to my lock-in amplifier. So now for the alignment, for the transmitter to correct for the misalignments, it needs to know whether the beam is misaligned in the first place. So this beam misalignment, whether the beam is present or not, is known by measuring the power at the receiver end. So there has to be a way in which this information of the beam misalignment has to be fed back to my transmitter side from the receiver side. So this information is, in our case, we are giving this feedback via a separate RF channel. And since there is no actual high-speed data that is being going over this RF channel, the speed requirements of the channel are pretty low. Like for example, in our case, we are sending this link feedback only at speeds of 350 bits per second. Now we'll see why do we need an additional amplifier at the receiver end. So now if I come back to the original misaligned case, so if we see here, the power at the receiver end is only because of this small intersection of my power, which is shown by this light blue curve here. So already the powers are very low at the receiver end in microwatts. Now, since there is only some part of laser falling on the optics, the power received is even lower. So now if my sensitivity of the receiver is not high enough, then I won't be able to get any power at my receiver, and I won't be able to steer the beam and correct for the misalignment. So that's where my lock-in amplifier comes in, which is able to increase the sensitivity of my receiver. So the graph here shows the response of my receiver with and without the lock-in amplifier. So the x-axis here shows the power, which is decreasing from left to right. Now this blue curve you see here is the response of my receiver without the lock-in amplifier. And in this case, the minimum power that we are able to detect is around minus 21 dBm. But as soon as we add my lock-in amplifier at the receiver side, this sensitivity goes up by 11 dB, which is around 92% increase in my sensitivity. So this is good. This is what we want, a good sensitive receiver. Now, if I again come back to our setup, you will find it difficult to see where is my actual high-speed data that I was talking about initially, because the only frequency you are seeing here is the 65 kilohertz, which is not high speed by any means. So the thing is, this 65 kilohertz is the modulation frequency of my 1310 nanometer wavelength, which is used only for the alignment. Once I get the alignment, once I get a free space link, over this link I will be able to send the actual high-speed data using multiplexing. That's exactly what we are doing. We are using wavelength division multiplexing, and over the same link, we are sending high-speed data over a different wavelength of 1550 nanometer. So at the transmitter side, we are multiplexing both the wavelengths, and at the receiver side, we are separating them using demultiplexing. Now, since both these wavelengths are quite far apart over the frequency axis, even though both are traveling together in free space, there won't be any significant interference between them. Now, coming to the actual experiments to see whether our alignment system is able to recover the link. So what we did is we took a free space link and misaligned it in such a way that there is no laser falling on my receiver optics here. So this XY plane you see over here is the receiver plane that I was talking about. So initially, since there is no laser falling, the power is 0 here. So the z-axis is the lock-in amplifier's output voltage, which, as I said earlier, shows the received power. So I go from this case to this case by searching for the approximate location of my receiver. So what the transmitter does is it searches for the receiver optics in 2D plane by performing a coarse inward spiral scan like in this fashion. So once I get the approximate receiver location, that means I get to a point where some part of my transmitted beam is falling on my receiver optics, then I can start my fine scan, which is the steepest gradient descent in our case. So this is the optimization algorithm that I was talking about earlier. So if you are able to see the blue dots over here, so these are the steepest gradient descent steps. So with each of the step of my SGD, the power at the receiver side is increasing, and ultimately I am settling at a maximum power location. So that means I was able to recover my link after the misalignment. So after this link recovery, we were able to receive the actual data, which was 2.5 which was sent at 2.5 gigabits per second speed, and we were able to maintain a get a bit error rate of around 10 to the power minus 11. So to put things into perspective, in wireless communication, bit error rates less than 10 to the power minus 9 is considered excellent. So that means our recovered link is pretty reliable. So all in all, we saw how our lock-in amplifier is increasing the sensitivity of my receiver, which in fact is helping to eliminate the need to split the beam at the receiver and do the alignment in that way. So our solution of lock-in amplifier is able to act as an add-on, which can be used in any of the existing alignment systems. So to summarize, we saw what is free space optics, how it is helpful, and how it requires a stabilized line of sight to work, and how our proposed alignment system is recovering a misaligned link in a more power efficient manner. Thank you.